Yes, excellent. Okay, hello everybody, thank you. Thank you for the very nice introduction. I am at both of these places, and I'm going to tell you about robots that can adapt like natural animals. This was a paper that we had in Nature in 2015, and the work was led by my excellent collaborators, Antoine Colli, Jean-Baptiste Mouret, and Dinesh Terapur. So, the general idea is that we all know that robots have gotten really amazing, and they can do all of these wonderful things. But if we want to deploy them in the real world, especially in dangerous environments, we have to deal with the inevitable fact that these robots are going to become damaged. So what would happen to the robots I just showed you if they become damaged or if the environment changes in some way? In most cases, they're not going to work very well. So the classical approaches to robot damage recovery are remarkably unsophisticated. You have to have this very extensive, expensive suite of sensors to catch all possible ways that your robot might become damaged. Then, if you catch that right type of damage, you have to take off of the shelf a pre-programmed contingency plan or a learn policy for that particular situation. And we can all imagine that that is very expensive, it's error-prone, it's manual, and it's just not going to scale to the complexity of the robots and the tasks that we want to deal with. Now, there are modern learning-based approaches that, including some of the work that we've done, but the problem is that those approaches only work on simple robots with low-dimensional state and action spaces, and they still require lots of real-world trials, and often that means that you end up breaking the robot instead of actually fixing it while you're flailing around trying a whole bunch of wild and crazy stuff. So, animals, in contrast, where we take our inspiration from, they act very differently in this situation. They have intuitions about different ways to move, they conduct a few intelligent tests, and then they pick a behavior that works despite the damage. So imagine if you're in a forest and you sprain your ankle. The first thing you do is you realize that your ankle doesn't work anymore, it hurts, and you might try a radically different kind of gait, like walking on the ball of your foot. And you might say, ow, that still hurts, it doesn't really work. So you will then switch to a different, entirely radically different type of gait, such as hopping on one foot, and you might say, aha, that's good enough, and you hop out of the forest, you go to your car, and you go to the hospital, and you get repaired. So we want robots to do that same thing. We want them to, if they become damaged in the field, to conduct a very few number of tests and either limp back to the repair station where they can get repaired and sent back out, or soldier on with their mission despite the damage if their repair was successful enough. So if we want to automate this pipeline, then we need algorithms that do each of these three things here, and I'm going to tell you how we do that. The first is getting intuitions on very different ways to move. And to do that, we need an algorithm that's good at producing a diverse set of high-quality solutions. And as the introduction alluded to, the best algorithm that I know of to do that is evolution. Evolution produced all of the different species that we see in the world, and each of them is very unique, but in its own way is high-performing at whatever it is that it does. So we are going to try to harness that. But that raises the question, whoa, that was crazy. That raises the question of whether or not evolutionary algorithms in computers are actually, in fact, good at producing diversity. So here's work that we did in 2013, where we gave evolution these building blocks, and its job was to design robot morphologies that would run as fast as possible. And if you look at this video, what you'll see is this parade, this Noah's Ark menagerie of different animals that all solve the problem in very different ways, and it's kind of got that je ne sais quoi of nature, in which it's kind of, it's weird, but it works. But the trick is that to get the diversity that you see in this parade, we had to pull one organism from different independent runs of evolution. And that's a very expensive way to generate diversity. What we want instead is algorithms that will, every time you run them, generate a diverse set of high-performing solutions. So the neuroevolution community has kind of invented a family of algorithms that go by two names, either illumination algorithms or quality diversity algorithms. And there are two major algorithms so far in this camp, and I'm going to introduce you to this one, MapElites, which stands for the Multidimensional Archive of Phenotypic Elites. So the idea here is that you might be searching in some really high-dimensional search space, like the space of all possible neural networks. But really, there are a couple dimensions that you care about of variation. For example, you might want things that have different fuel efficiency, or different cautiousness, or different speed. And so you might want to see the possibilities along those dimensions of variation. So you pick dimensions of variation that you care about. In this example, to be the height and the weight of the robot. And then we're going to look for the best possible, the highest performing thing at every point in this grid. So here's the algorithm. It's exceptionally simple. You generate a random solution, you evaluate it, you get its phenotypic attributes, which are these behavior characteristics, such as a height of 4 and a weight of 7, is performance, which we call fitness, and you put it in the right bin. Then you take something out of the bin, randomly perturb it, and then you see where should it go in the bin now. It might be different, so it might have different phenotypic attributes, like a different height and weight, and then you score its performance. And if it's better than the current occupant of that cell, you swap it in, otherwise you throw it out. And then you just repeat the process over and over. And the hope is that this algorithm will therefore return the set of high-quality solutions throughout the entire space, which might look like this. So we ran this algorithm on this soft robotics problem. Again, we're doing morphologies, and the dimensions are the number of voxels on one axis and the percent of this bone material on another axis. And what you see here is that a classic evolutionary algorithm does not search the space very well, and also the performance is not very high. If you add diversity to evolutionary algorithms, which is known to improve performance, you do indeed get higher performing solutions. You'll notice those are yellow dots now, but it still hasn't explored much of the space. Map elites, in contrast, is a sea change in what is possible now with search algorithms. That you don't just find one solution in there that looks pretty well, and you look at the history to see what your diversity is. You're actively exploring the entire space of possibilities, and you get you can see why we call them illumination algorithms. They illuminate the space of possibilities. For example, you learn what's the best that you can do in this corner. You find these two different modes of solution that both look like they're high performing, et cetera, et cetera. Now, I want to point out, this and this have the same number of evaluations. It's just telling you how little we've been exploring so far with a lot of our search algorithms. And the same thing would happen with reinforcement learning if that's your favorite algorithm. So here is an actual walk through the space of possibilities from one of the runs of this algorithm. What's really cool is that, like in nature, you see kind of like family relationships. So you find this organism here, which is one style of robot that goes here, and as you sweep up this peak here, you see the same basic motif, but translated into having more blue bone material. So it's almost like this is like the brothers, and then the cousins, and then the distant cousins, et cetera, or different families of dogs or cats and whatnot. So here is the robot that we will be conducting our experiments on. It has 18 degrees of freedom and has all of its computation and sensing on board. And the way that we described the behaviors we were interested in this particular domain was the percent of time that each leg touches the ground. And since it's a 6-legged robot, that means it's a 6-dimensional cube, a hypercube that we're trying to fill up. And we're doing this all in simulation. Now, producing and filling this map, which you can actually see here, we're visualizing it in 2D. Filling this map is quite expensive. It took about 2 weeks on a modern, powerful computer. But you only have to do that once ahead of time for each robot, and then you can ship out 1,000 of these robots with that map. And also, as I mentioned, the search space for this robot has more possibilities than there are molecules in the solar system, so it's a huge space. And the map ends up having 13,000 roughly behaviors that are all pretty high performing and yet different. And importantly, in the map, we know kind of the distance between gates, such that nearby gates in the map are similar to each other. And we'll harness that in a second. So now we have the yellow block. Here are some examples. This gate here uses that leg that was circled about 10% of the time. You could have another gate that has to use that leg 20% of the time, 30%, 40%. This one uses that front left leg 10% of the time, and we have all possible combinations. One interesting corner case, in this case literally, it's a corner in the hypercube, is the cell that tries to walk without ever touching its feet to the ground. We actually thought that this would be impossible, and we expected it to be 0. But sure enough, evolution shows us that it is cleverer than I am, because I did not anticipate this particular solution, which is pretty awesome. So now we've got our intuitions of different ways to move in the world, and now we want to conduct a few intelligent tests. Now, the question is, we learn things in simulation on this robot, and now it's the real world and the robot is damaged. It's game time. The clock starts ticking. So what of these 13,000 things should I test on the robot? Well, you might say try the top-end solutions. But they're all might be very, very similar to each other. And if one of those doesn't work, then probably all of them won't work. Instead, what we want to use is Bayesian optimization, which is a very data-efficient algorithm, to test one family of algorithms. If it doesn't work, rule that family out, try a different family of algorithms, and move around the space. So more concretely, if you're familiar with Bayesian optimization, our prior expectations for how each gate will perform in the world come from the simulator. That provides us with our predictions. But we update our posterior understanding of how well these different gates perform based on real-world tests. But we don't just update that cell. We update the nearby cell as a function of the distance in the map, because that tells us how similar these different gates are. And then we stop when we get a behavior in the real world that's better than 90% of what remains in my map. So here's a one-dimensional example to make it a little bit more concrete. Offline, ahead of time, we were in map elites. Here we have a one-dimensional behavioral descriptor to find the best possible gate across this entire dimension. That gives us predictions, which is this green line here, of what's going to happen in the real world if I tested each one of these gates. But also, because it's Bayesian optimization, we can model the uncertainty about my prediction, which starts out as uniform, a uniform amount of uncertainty. Now, imagine that this is the real performance on the damaged robot. We don't know that in the real world, these gates are all going to be terrible, and this is the best gate. So we'll try this gate first. We'll update once we get the data back that says that's actually terrible. Lower the mean prediction and the related and the uncertainty. We're now perfectly certain that that sucks. And then we will say everything nearby, we will update the mean and the uncertainty as a function of the distance in this space. So then we will try the second behavior. That actually works pretty well, and that's better than anything really I think remains in the map, so I will stop. So that was a quick example. So let's see how it works on a complex solution, which is the six-legged robot. So here is the undamaged robot with the classical tripod gate. This is a hand-coded gate. Note that it goes straight to the right, and it's 0.25 meters per second. Now the robot becomes damaged. A brick fell on it while it was looking for survivors, for example. And now its original behavior no longer works. It's 0.03 meters per second, and it's curved. So now the robot needs to adapt. So start the clock. And in fact, the clock is in the top right-hand corner. We will try one thing from the map here, and notice all the red and orange. We think that's going to work really well. It actually doesn't work very well. It's 0.13, so we'll update the map to reflect that, and you'll notice the map became a little bit more blue. It's a six-dimensional hypercube, so distant things are also turning blue, because distant things are nearby. But now the second thing we try updates the map again, and now we're on our third gate, we're on to 0.17 and an almost straight trajectory after 18 seconds. In 19 seconds, much of the map is now blue, but we still think there are pockets that might work. This one's getting pretty good, 0.2 meters per second, almost straight. And now, in 26 seconds of real clock time, we have a robot that is limping itself almost at the original speed, 0.24 meters per second, and almost perfectly straight, and the algorithm could stop there. If you look at this gate in slow motion, it looks natural. It looks kind of like it's using dynamic motion to deal with the fact that it's got this dangling leg, and it almost looks like a wounded crab that's running away from whoever stepped on it. In fact, a lot of the YouTube comments on these videos were sympathizing with the poor robots that we harmed in the making of our research. So did it again. So we tried this algorithm on 6 different damage conditions, and in almost every case, intelligent trial and error, which is the name of our algorithm, in blue, outperforms the original gate, which is yellow, and it does so in about 1 to 2 minutes and between 6 and 15 experiments in the real world. That's it, and figures out a compensatory gate. We tried a lot of different controls, including policy gradients and Bayesian optimization in the original search space, which remember is huge. It's more molecules in the space than there are in the solar system, and that works terribly. These algorithms don't scale to these high-dimensional spaces. But if you launch those algorithms or intelligent trial and error or Bayesian optimization in the low-dimensional space found by Map Elites, the 13,000 map, and you use the knowledge of where, like the distance function and the predictions from simulation, that's when you perform the best. So all of these algorithms up here use Map Elites, and the green one is the one that uses all of the pieces that I introduced to you. The same exact algorithm will work on a different robot. In fact, we believe on many different robots. Here's a more traditional factory arm, for example. It knows how to pick and place. One of its motors becomes disabled. We actually tested 14 different damage conditions, including multiple motors being disabled. And obviously, no longer it places it according to the original policy. And so now the robot will adapt in real time. Again, the clock is up here. And you could imagine, instead of bringing down an entire factory floor to go repair a robot that's on the floor that's no longer working, now you could let this algorithm run in real time, and in about 20 seconds, this robot here, I think it's 23, figures out a policy that can place, again, despite the fact that it's injured, and then maybe only infrequently you bring down the factory floor, and you go replace all the broken robots, and then you bring the factory floor back to life. You've dramatically reduced your downtime. I also want to point out that there is no fundamental difference between adapting to a different body and adapting to a different environment. It's still just domain shift between what you trained on and what you're currently seeing. So if you change the environment, we show in our paper, this same algorithm will just adapt to a different environment. None of the work that I did so far involves deep learning. We use simpler controllers to make our point, but I actually always thought somebody's going to take this algorithm and just plug in deep learning, and it turns out somebody did. So here, Kumi et al. Took the exact same algorithm, and they swapped in deep reinforcement learning to learn the policies to fill the map, and then the rest of the algorithm is just straightforward. Here is DDPG, the algorithm we heard about in the last talk, and the original policy, once damaged, cannot walk at all. And here is their version of the map elites, the intelligent trial there, and after a few trials, in this case 3, it's moving on and doing quite well. And you can see that they basically have the same machinery going on under the hood in their video summary of their work. And you can even see the same map plotting scripts going on to show you that they also have this kind of 6-dimensional map, and things work quite straightforwardly. Here, they do a demonstration of the original policy, which I believe was not trained with stairs, and then they put it on with stairs, and in 12 trials, which is, I guess, 600 seconds, now they found a gate that can still walk in the world with stairs. And then who doesn't want to watch somebody learn how to walk with a club foot? This robot was not trained with a club foot, I believe, and figures out a funny-looking gate that still works despite having a huge cast on its foot. Just endlessly entertaining to me. Okay, so you could also, instead of swapping in policy gradients, which they use, you could also swap in deep neural evolution itself to train the neural networks. Because again, even though neural evolution tends to be sample inefficient, this is all happening in simulation offline ahead of time, so you don't really worry about the cost of that. We recently had a blog post out of Uber where we introduced 5 different papers that make the point that neural evolution algorithms are kind of are starting to also benefit from a lot of the modern computation that's out there, and you can really supercharge them, and they can do fantastically well. And what we show is that they actually can be competitive with modern reinforcement learning algorithms like DQN and policy gradients, for example, on learning to play Atari or having robots learning to walk, et cetera, et cetera. So that's basically whatever optimization you want to learn to use to learn your policies, you can fill the map with that, and then you can use the rest of the framework to perform quite well. So, in conclusion, I've introduced the intelligent trial and error algorithm. It is state-of-the-art in terms of robot damage recovery, and more broadly, it can adapt to any different situations, such as different environments, or other kinds of domain shift, such as simulation to real, etc. It adapts in about 2 minutes to damage that it encounters, and this is what I love about it. It combines the creativity of evolution or stochastic optimization or learning or reinforcement learning, whatever kind of stochastic optimization you love, that usually is very creative as long as you have lots of computation, but is very sample inefficient. But it combines those strengths ahead of time offline in simulation with the data efficiency of Bayesian optimization in the real world when the clock is ticking and you can only spend a few tests or trials because either the clock is ticking or because you might damage the robot more. It also shows the benefit of learning a diverse set of high-performing solutions. So this notion of these quality diversity algorithms that try to learn a set of high-performing, high-quality things, this is not the only use of those kind of algorithms. Imagine what you would do with a repertoire of all those primitives. In fact, in previous talks, we saw these other approaches that can generate a repertoire of primitives. You can do hierarchical RL on them. You can use them for a variety of different tasks. And I actually think that that's an exciting area of future research, which is exactly how to best harness sets of high-quality, diverse policies and primitives. With that, I'll say thank you and also thank my collaborators.